Welcome to Chapter 3. In this chapter, we will discuss equations that use the z-table and the t-table. Normal distribution. The standard normal distribution is a normal distribution with the average equal to 0 and the standard deviation equal to 1. A random variable with a standard normal distribution, denoted by the symbol z, is called a standard normal random variable. Below, we have the probability distribution for a normal random variable x. Through these equations, we are also able to achieve the transformation of z equal to x minus the average divided by standard deviation. Now, why would we want to use the z-table? The z-table is short for the standard normal z-table. The standard normal distribution is used in hypothesis testing, including tests on proportions and on the difference between two means. The area under the whole of a normal curve is 1, or 100%. The z-table helps by telling us what percentage is under the curve at any particular point. For example, if you had a box of 100 7-ounce bags of M&Ms, how would you find the minimum and maximum of a certain color per bag? The procedure, located in the top right corner of this slide, tells us that when x is given, we can use the z-table to find the probability. When the probability is given, we can use the z-table to find the number of x. The steps to solve problems start with number 1, reading the question and extracting the following information: x bar, or mu, the average, and standard deviation, or sigma, the variance. This information can be in the form of data, which you have to make a list of and use your calculator, or in the form of x, n, mu, sigma, which are given. The second step is to graph the bell-shaped curve and shade the required regions. If x is given, use transformation to find z, and go to step 4a, using the table to find the probability, or p of z. If probability is given in step 3, use the table to find z. Then go to 4b, use transformation to find x. The equations for a and b are on the bottom of this slide. Now, let's learn how to read the z-chart when z is greater than 0. First, find the ones place and the tenths digit of z in the first column to find your row. Then, move your finger right to the column of z in the hundredths digit to find the probability of the area. In case your z is less than 0, you will have to use the other chart that deals with z's negative numbers. You will still have to start with your finger on the left side in the ones place and the tens place, moving it to the right to z's hundredths place to find the probability. When you don't know the z-chart value, Find the closest percentile in the chart to locate your z value. In the first example, the probability of z being equal to 0.7967 is inside the chart, so you move your finger to the left to find 0.8 and go straight above to find the hundredths place, so you will have z being equal to 0.83. The second example has a probability of z being 95% or 0.95. This number lands in between two other numbers in the z chart. Still, having your finger go to the left, you will find 1.6, and going straight above between those numbers, you will get the combination of 4.5 in the hundredths and thousandths place, leaving you with z equal to 1.645. The last example has the probability of z being equal to 99% or 0.99. We find this in the bottom right of the z chart, where two numbers have the same percentage. So you can use either 3.08, 3.09, or the average of the two being 3.085. Use the z-chart when your sample size is greater than 30. Example: the following data set gives grades in an exam for Math 10. When we add up each value of f, we will receive our sample size, or n, being equal to 164. Let's dive further into this data set to figure out the minimum grade in the top 10%, the maximum grade in the bottom 0.7 or 70%, and if this class was curved, a person with a grade of 67 would receive a C, and with a grade more than 87, they would receive an A. So what would the grade be if a student scored 76? For the first part, we need to graph what the minimum grade would be in the top 10%. So we shade the right side of the graph, and we plug in the data information that we know, where the average is 52.56, the standard deviation is 26.5, and the probability of z is 90%. We know this because 10% being on the far right, subtract that from 100% and you get 90% being everything on the left side of our score, which is noted as x. To find x, we need to figure out what z is. And to find z, we use the chart. The closest percentile we can get to 90% is 0.8997. Going to the left, we use 1.2, and above, you use 8 in the hundredths place. With z at 1.28, we use the equation of z equals x minus average divided by standard deviation to come to the conclusion of x being equal to 86.48%. In this second part, we want to know the maximum grade in the bottom 70%. We start by drawing the bell graph and shading the appropriate region which is the left side of where x is. We still know that the average is 52.56, standard deviation is 26.5, but this time the probability of z is 70%. %70 falls in between these two numbers, so we can use the combination or the average of 0.52 and 0.53 to come up with our z as 0.525. With this new data, we can complete our equation to solve for x being 66.47%. In this last section of the problem, we will have to figure out the percentage of z. This time, we are given that the score is 76. The average and standard deviation are still the same, but z is going to be 0.885 after we plug all that information into the equation. Now we can look at the z-chart. We begin at the column on the far left, 0.8. We go all the way to the right in between 8, 9 at the top, which is the hundredths place, to find the in-between of 0.085, which will fall in between these two numbers. When we average these two numbers, we can get 0.812 or 81.2%, which is a solid B. Use the z-chart when your sample size is greater than 30. But what if my sample size is less than 30? We use the t-table to find a standard normal random variable when our n value is less than 30. It's like trying to figure out how many cute puppies can fit inside of a basket.
Okay, so now I'm going to teach you how to read and use the t-chart. First thing you should remember is that you use the t-chart when your sample size denoted by n is less than or equal to 30. So every time you have a sample size that's lower than 30, you should use the t-chart. This number here, to this column here, to the right, is your degrees of freedom. Degrees of freedom will be denoted by lowercase t, lowercase f, is your sample size n minus 1. So let's say you have a sample size of 16. Your degrees of freedom would be 16 minus 1 equals 15. So your answer would be somewhere on this row here, because of the 16 minus 1.
The t-chart is almost read the same as the z-chart, except you have to find your degrees of freedom on the far left, and then alpha. Alpha is given in each problem either by figuring out what alpha is, or alpha is just straight up given to us. If no alpha is mentioned, we can assume that alpha will be 0.05. Let's find the t-table. Remember, your t-table is a combination of the degrees of freedom and alpha, where degrees of freedom is n, your sample size, minus 1. In the first problem, you have n being equal to 25, which makes your degrees of freedom 24. Starting at the 24, move to the right till you reach the alpha column of 0.025 to find your answer at 2.06. The second problem starts out with 17 as your sample size. Subtract 1 to start out with 16 degree of freedom. Go all the way to the right to the 0.005 alpha column and find 2.92 to be your answer. The last equation just says that the sample size is 2, which means your degrees of freedom will be 1, and if no alpha is given, we assume it's 0.05, bringing our answer to 6.31. When reading the t-chart, you begin the same way you read the z-chart. The first step is to draw your graph and chart where the t value should go, which is on the right side of the average. Second, go to the first column of the t-table and locate the corresponding degrees of freedom. Third step, follow your newfound degrees of freedom to the next portion of the chart in the alpha column. Now match up your alpha value to the corresponding column. Follow your corresponding value to match both your degrees of freedom and your alpha value. You want to make sure you got it right the first time. Now, write the t-table for the appropriate shaded region. Let's practice. Now let's find the t-table and graph it. For the first equation, let's have n be the number of people listening to this presentation. So about 11. Alpha will be 0.01. We will start with our degrees of freedom at 10, moving it to the right to the 0.01 alpha column to find our answer at 2.76. On the graph, you will notice that the shaded area is 0.01, the alpha, which means that the non-shaded area is 0.99 or 99%. The second equation will have n as 22 and alpha be the probability of x being greater than 90%. To graph it, you will notice that the left side, 90%, is not shaded. Since we want to know x being greater than that, the shaded part is on the right, to bring us to our new alpha at 0.1 or 10%. Degrees of freedom will be 21, and we move to the 0.1 alpha to come up with our answer at 1.32. Notice, shaded alpha is to the right of the average. By replacing our z-chart with our t-chart based on our sample size, we replace our z-cal with t-cal in any equation. It's so easy. The following is brought to you by Chapter 3 Theorems. The approximation of binomial to normal distribution tells us that when n, the number of data, is large, a normal probability distribution may be used to provide a good approximation to the probability distribution of a binomial random variable. Remember that the average and the standard deviation in terms of n and p our mu is equal to n times p. Sigma is equal to the square root of n times p multiplied by 1 minus p, with conditions that n times p is greater than 10 and n times 1 minus p is greater than 10. Example: in the last 10 years, there was 60% of the students taking Math 10s being female. If there are 40 students in a Math 10 course this year, A, what is the probability of at most 29 females in the class? And B, what X value gives probability of 70%? So we know that n is 40, our probability is 60%, so mu is 40 times 60%, which is 0.6 to make 24, and sigma will come out to be 3.0984. Draw the curve and indicate the mean and random variable x. Now we will use our z equation, where z is equal to x minus mu divided by sigma. Given z value, you can now find the probability of less than z from the table. Z is 1.61, corresponding to the probability of 94.52%. In normal distribution, the central limit theorem helps us measure the accuracy of our statistics. This theorem gives us the ability to measure how much the mean our samples will vary, without having to take any other samples to compare it with. By taking this variability into account, we can use our data to answer questions about a variety of things such as population. We will do this using confidence intervals and hypothesis tests, respectively. The larger the sample size, the better the approximation to the sampling distribution of x bar will be. When dealing with these sample sizes, we will use the equation of z being equal to the x bar minus mu divided by standard deviation divided by the square root of n. As stated before, when the sample size is smaller than 30, you will use the same equation for the z, instead replacing z with t. An example of using a small sample size would be the following question. The mean of test grades in a math class is 81.2 and the standard deviation is 20. Find the probability of grades above 70 if 25 students' scores are selected. So we know that x bar is 81.2, the standard deviation is 20, and the sample size is 25. Using t equals x bar minus mu divided by standard deviation divided by radical sample size, we can get the below equation to find out that t is equal to 2.8. Using the graph to the right, you will notice that t is the left side due to 70 being on the left side of the mean 81.2. Now let's go to the t chart to figure out the percentage of t being 2.8. With our sample size at 25, we will begin with our degrees of freedom at 24. We start in the row 24 and move to the right until we find 2.8, or the closest t-cal to 2.8. Then we will go up from there to find our alpha, or percentage, at 0.005, otherwise known as 0.5%. Going back to our example with this newfound information, we now know that the unshaded part is 0.005, which leaves the rest of the graph being 100% minus 0.5% to bring us to 99.5%. To find the confidence interval, we need to know the percentage of the confidence interval. Then the leftover percent, which would be 100 minus the confidence interval, will be our alpha. Divide that into 2 to find the shaded regions on the left and the right side of the confidence interval. We use the equation of the mean minus standard deviation of the z or t chart times by alpha divided by 2 in order to find our 2 points for the confidence interval. In case the information on the previous slide was a bit confusing, let's do an example. Let's have the confidence interval be 90% with the standard deviation of 6.5, the sample size being 144, and the mean at 0. At first, we notice that the tails are 5% each. This is because 100% minus the confidence interval of 90% leaves us with 10%, and we divide that in half to make 5% for each tail. This also shows us our random variables A and B that we need to find in order to finish this problem. First, we noticed that the percentage of random variable A is 95% because of the left side tail plus the confidence interval equaling to 95%. The random variable B has only a 5%. Let's go to the Z chart and figure out the 95% Z-cal. We start by locating 95 percentile within the chart, which is here. Then we find the ones place and the tens place being 1.6 and go up from the same percentile to find the hundreds place between 4 and 5. This leads us to Z being 1.645. Now that we have z being equal to 1.645, we can finish this equation by inputting all of the data. We will start with the mean being 0, subtract our standard deviation and the square root of our sample size, so that's 6.5 divided by square root 144, and multiply that by our z, which is 1.645, which will find us our random variable b on the left side of the mean. The right side of the mean will have 0 plus 6.5 divided by square root 144 multiplied by 1.645. Below, you will find the answer for random variables b and a being negative 0.89 and positive 0.89 due to the mean being 0. Fun fact, our error bound is our z multiplied by our standard deviation divided by the square root of our sample size, being 0.89. As you can see on the graph, 0.89 is the same distance from the mean on the left and the right side. This brings us to determining the sample size. In order to estimate the average to within an error bound with a confidence level percentage, we can use the equation below to find the error bound. Error bound will be equal to the z calculation of half of the alpha multiplied by the standard deviation divided by the square root of the sample size. In order to estimate the sample size with an error bound, we can find the minimum sample size by using n is equal to the z-cal of half the alpha squared multiplied by standard deviation squared, all divided by the error bound squared and standard deviation squared. Or in short, the z-cal half of the alpha squared divided by the error bound squared. From all of the useful information given in this presentation so far, we should all be able to complete the following practice problems together.
Alright, well, so let's do an example. Let's say you have a class with an average weight of 120 pounds, 120.3 pounds, with a standard deviation of 15. Find the probability of the student's weight being less than 130 in a sample of 16 students. So the first thing you would have to do is, or that you can do, is define the variables. Going from left to right, we see that the average weight is 120 pounds, so the mean is 120.3 pounds. Mean will denote as x bar equals 120.3. Standard deviation we will denote as sigma x equals 15. And we're trying to find the probability. We'll denote as x, or I guess is 130 pounds. And your sample denoted by n is 16 pounds. Second step is you would graph, or you would draw your graph. And because it doesn't tell you here, but we'll assume it's normally distributed. Normally it'll tell you if it's normally distributed or if it's some kind of different distribution. But because it's normally distributed, we know that it's symmetrical. So you make a symmetrical graph and you plot your points. Because it's symmetrical, normal, distributed, your x bar is in the middle, so 120.3. And what you're trying to find is the probability of x being less than 130, than or equal to 130. So you would find 130, which would be about here. And then because it's less than or equal to, you would shade this region. And this is important so that you know later on that your answer has to fall between here. Now, this would be your t-chart. Third step would be to find your t-cal. And we're finding t-cal because remember that your sample size is less than 30, and when it's less than 30, you use the t-chart. So you find t-cal with the equation x minus x bar over sigma x divided by root n. And because you already have the numbers, you just plug them in. So it's 130 minus 120.3 divided by 15 root 16. And then when you do the math out, you get 130 minus 120.3 equals 9.7 divided by 15 divided by 4, because the square root of 16 is 4, was 3.75, which is about 2.6. And this is your t-value. So now that you have your t-value, we'd have to find alpha on the t-chart. So you pull up your t-chart. So the first thing you would do once you open your t-chart or you bring it out is you have to look up the degrees of freedom. Degrees of freedom is always n minus 1. So your n was 16, so you'd go to 15. So your answer would be somewhere on this row right here with the 15. So you go look for the t-value that you found, which was 2.6 or close to it. But since we have 2.6 right here, you just go straight up. And your alpha is 0.1. So alpha is 0.1. Now you have to remember that t-chart, 0.01, sorry. You have to remember that t-chart gives you the numbers, would give you the numbers to the right. So your t-chart gives you this, but you want this side. And so to get that side, you'd have to subtract it from 1 so that you can get this value. So it would be 1 minus 0.01, so that you can get this one. So you get 0.99. So the probability of x being less than 130 pounds in the sample of 16 would be about 99%. And we get that because you multiply that by 100 to get the percent.
In this problem, we are given that the population of kids that are affected by Fragile X syndrome, a genetic disorder that causes learning difficulties, has normally distributed with a mean of 70.5 and a standard deviation of 8.9. We are to find the probability of affection below 72 in a group of 100 kids, construct a 92% confidence interval for a mean of 100 kids, and find the minimum sample size for an 87% confidence interval and error bound of 0.03. We can begin part A by drawing the graph that is on the right. We know that our mean is 70.5, standard deviation is 8.9, and that we have 100 kids. We want to find the percentage of x being under 72. We are going to use the equation of z is equal to x minus the mean divided by standard deviation, and by using the information that we have, we can calculate z to being 1.68. Now we move on to the z-chart. Starting at the 1.6 row, we move all the way to the right to the number 8, which is the hundredths place of our z, to find 0.9535. Let's double check the percent that we found with our shaded area of the graph and conclude that our answer is 95.35%. For part B of this practice problem, we will construct a 92% confidence interval for 100 kids. The mean will stay the same at 70.5, standard deviation will still be 8.9, and our number of kids will still be 100. This time, we started out with the graph at 92% in the middle, leaving us with 4% for each tail. Let's find point A. Point A gives us 4%. Now we look in our z-chart for 4% or 0.04. And we can notice that this z-chart doesn't have anything below 0.5. So let's go to the other z-chart. Okay, that's better. So we can locate 4% about here at 0.0401. To the left, we will find negative 1.7 for the beginning of z, and above 0.0401, we will find 5 for the hundredths place, which brings us to z being equal to negative 1.75. Once again, finding z will complete the data needed to finish off the equation. We can now plug in the information to find the equation on the right and transform it to figure out point A, shown as below. A is equal to negative 1.75 multiplied by 8.9 divided by the square root of 100, adding the mean of 70.5. This brings us to point A being 67.44. We can also use point A's information to find out the error bound by subtracting it from the mean to get 3.06. By adding 3.06 to the mean, we will find out point B's answer on the right side being 73.56. Now we have concluded the confidence interval with the answer shown at the bottom. For part C, we will find the minimum sample size for 87% confidence interval and an error bound of 0.03. With an 87% confidence interval, we are left with 13%. divide that in half to find each tail to be 6.5%. Looking into our z-chart, the 6.5%, or 0.065, is closest to 1.52. Plugging in the z calculation of alpha divided by 2, we will find n to be 1.52 squared divided by the error bound that is given, 0.03 squared. After calculating, we find our answer to be 2,567. This concludes our Chapter 3 summarization presentation. If you would like to replay this presentation, please continue clapping.